So how does RAW plan to achieve its goal of enabling over wireless links the service level agreement of a packet delivery ratio within bounded latency? For instance, right? Reliability could be expressed in different terms, but that's the typical term in which we would express it. Well, basically, the engineering balance that we have to find is optimize the tension between, on the one hand, reliability and availability, which means A, try to send the packet on as many paths as possible with all the possible redundancy that you could have, which means basically use everything that the path computation element has given you, the routing element on your network. And on the other hand, try to minimize the use of constrained resources, and the two most constrained resources we have in these networks are the battery of the device, if you have a relay or phone or something like that, and the spectrum, which is a bounded resource as well that you have to share with all the other transmitters. So how can you optimize the use of those constrained resources and still guarantee the SLI? So if you take a traditional SDN structure, you have this controller up there which computes the path, provides redundancy if needed, and you're all set with your deterministic network. But with wireless, there are two things which change dramatically. On the one hand, the latency between the controller and the device can change because you have to talk to this device maybe over a wireless mesh, which can be slow, or to a phone. So it's not just like controlling a data center next to you. The latency to get there can increase dramatically. And the other thing is that the links flap a lot more often on wireless. They flap all the time, and they flap for flip seconds. So what you cannot do is, from the controller standpoint, fix every prime as they come. So the controller, this path computation element, has to provide the wireless device with more redundancy than actually needed, so as at every point of time there is enough redundancy. But if the wireless device uses all that redundancy that the network controller has given, then it will considerably waste energy and bandwidth, because maybe one of those links is really operating well and you don't need to transmit over 3 or 4 other ones. You would be wasting spectrum and energy. So the raw prime is really to address that tension, and that tension has to be addressed in runtime, and the prime cannot be pushed to the path computation element because it does not operate on the same time scale. We have to operate instantly to any change in one of the links in a small graph, that this path between A and B that the routing has designed, and we have to do it locally without going back to the routing. So to do that, we need two main elements. We need to measure from the inside this very small network subgraph between the ingress and the egress. That's when OAM comes into play. So OAM being the capability to send frames that will observe the links, or maybe to insert headers in the packet that will trace the quality of the links, for instance, that this packet has observed as it was being forwarded. And so we need to bring that information back to the source, or maybe to the nodes in between, so that everyone knows basically the quality of the rest of the way and can make decision on that. So that's the one thing you need to measure, so gauges. And then you need the knobs. You need to be able to signal in the packet what is expected for this particular packet within that particular graph. So you have a graph where you have multiple forms of diversity and redundancy. Which of them are used for this packet based on the most recent observation of the network? And this decision can be done at the source, the ingress, meaning that the ingress has a very recent view of all the hops. It knows the graph, and then it can flag in the packet what each hop is supposed to do, replicate to this neighbor and that neighbor, or just forward to that neighbor, etc. Or the decision could be distributed, in which case every node in the small graph knows the quality of the rest of the path and may make a decision to use this guy on the left or this guy on the right, or maybe both, to forward this packet and obtain the kind of guarantees that you want for this packet till the destination. And that's really where the raw work comes into play. If you take the traditional SDN operation, everything is done on this central engine that we call a PC, a path computation entity, which is basically the routing piece in your network controller, in your SDN controller. In the case of wireless, talking to him may be slow. The time scale at which it observes the network can be, it's a long time, like days, hours. Based on that, it will have a statistical view of the quality of every link. So it sees each link as a shade of gray. This link is rather good, like 80%. This one is not as good, like 60 and less than 50%. I'm going to use two of those three links to say that in average I get, I don't know, 2 packets arriving at the destination. So you need to have some kind of guaranteed redundancy here to cope with the accidents of transmissions. This PCA will look at a very large network. It will look at the overall network, and inside this overall network it will make decision of this guy uses this and this guy uses that, so as to share globally the resources in the network. It has a kind of a God's view, but very averaged on a very long time. And so it will take slow decision to actually change a path between A and B. And it will, to do that, it will use metrics which are not reported like every split second, but are reported maybe every minutes, hours, etc. This is fine for wires because wires are very, very stable. This doesn't play well for wireless because a wireless link may flap for a split second. So if you get hundreds of wireless hops in your network, I mean, the PCA would just be overwhelmed by route recomputation, and anyway it would not have the bandwidth to send the new routes in time to the network so that everybody does the right routing decision. So what RAW has to do is split the work between the PCE and a new engine that we call the PSE, the Path Selection Engine, which is where we'll make the decision of whether we use this form of diversity or that form of diversity, so we can guarantee the SLA and minimize the consumption of spectrum and energy. The PSE decision can be source routed, and then the decision is tagged in the packet, or it can be distributed, meaning you look at the rest of the way. You have to know at a very short time scale the current status of the network to make the optimized decision. So the faster we'll know the current state of the network, the more we can save energy. So you see this balance about the amount of control. How often do I measure my network? And the amount of traffic that will benefit from the latest measure, meaning that if I know very well, then I can have used less of that redundancy. So there is a balance to be found here. The PSE will be looking at a very small network, just one particular deterministic track, and this is where we will guarantee the SLA that we are looking at. So basically that gives you a good idea of what the group is about, what we need to do. We need to select radios. We have selected a number of them. We have to adapt how we use the diversity for a given packet, and we will have to find the signaling in the packets to tell, you know, what's the expected life for this particular packet in this particular flow within that particular graph, which is associated to the flow. And then we will have to define what kind of OAM needs to circulate, whether it goes in the packet in band or whether it's out of band, and what kind of metrics we expect to measure with this, like link quality information over each hop, or the ETX, or things like that. The work at the IETF has already started. We've got documents which tell you about the different radios. We have 2 specific ones for LDAX and 5G. If you care about those radios, that's interesting drafts. We've got raw technologies, which is kind of a catalog of all the technologies with less but the same information, so you can compare them. You can get an abstraction that would represent them globally that we can use at layer 3. We've got use cases. Then we have started the work on requirements and on the architecture framework for which we are chartered. And we also started what we expect to do really, which is to push work on the working groups which work on specific tools like VIR.